All right, now we're going to talk about the SN1 reaction. So the best way to talk about all these mechanisms is to do an example. The quintessential SN1 example that everyone talks about is this one. Tertiary butyl halide in a polar protic solvent will give you an ether. Plus HBr. That's the quintessential example of an SN1 reaction. SN1, substitution, nucleophilic, so it gives me an idea of the type of reaction and type of mechanism. 1, unimolecular. So just like in SN2, the 2 meant bimolecular. Here the 1 means unimolecular. The 2 meant it was second order. The 1 means this is first order. So second order means there's 2 entities in the rate limiting step. 1 means there's 1 entity in the rate limiting step. Okay? SN1 reactions always form a carbocation. Always form a carbocation. One more time. Always form a carbocation. Always. SN2 never formed them. SN1 always forms them. That's how it works. Now let's talk about the SN1 mechanism. So let's draw the example up here. So I'm just going to redraw the reaction so we have a reference point. Using a polar protic solvent. A polar protic solvent. You get the ether. And HBr. Okay, so that's the reaction. Now let's talk about mechanism. What's the first step in the reaction mechanism? Well, it's the bromide leaving to form the carbocation. And that's going to be an equilibrium reaction. As the carbocation forms, of course, the carbocation can reattach itself to the bromide and you go back to where you started. But of course, that doesn't lead to product. Cation on the carbon plus the bromide ion. All right, so it's bromide, so there's negative charge. Now, that's step number 1. Step number 2 is a nucleophile attacks the carbocation. So step number 2, now I'm just going to redraw the carbocation down here. Normally, if I wasn't going trying to emphasize the steps, I would just do it next. I will just use this drawing and go on. But because I'm trying to embellish the steps for your notes, I'm going to redraw it. If you do it on an exam, you redraw it, it wouldn't bother me. I wouldn't care. You're just wasting your time, though. You can just continue on from this drawing up here. But for sake of your notes and for this lecture, I will redraw it down here just to be crystal clear on what's going on. All right, so now the cation forms. So now the solvent, the methanol, remember this oxygen is delta negative, right? Is going to be highly attracted to that cation right there. So the cation and the delta negative oxygen are going to collide. And when they do that, these electrons will form a bond with that carbon. And then bromide, or the solvent, I use bromide because we have HBr as a product, but it could have been the solvent. You could have used methanol to do this next step. We'll deprotonate the ether, giving us the product. And there you go. There's the mechanism of an SN1 reaction. It's a two-step mechanism. SN2 was a one-step concerted mechanism. SN1 is a two-step not concerted mechanism. SN2 does not form a carbocation. SN1 must form the carbocation. Let's do a second example, because if one example is good, two examples are better. How about this one? And we'll react it with methanol. Any alcohol will do this, but methanol is convenient because it's small, easy to draw. Okay, so step one. Leaving group leaves. And that's going to be an equilibrium. Carbocation forms. No problem. Leaving group leaves, carbocation forms. Solvent attacks. There we go. So now we've made the protonated ether, which now I'm going to use the solvent this time to deprotonate. So more solvent molecule comes around. Now, why wouldn't I use the bromide? I mean, I could. But logically speaking, it's probably going to be the solvent that deprotonates. First of all, because there's a lot more of it. And second of all, because bromide is the conjugate base of a strong acid. It's a good leaving group. So it's not very acidic. There you go. So there's another example of the SN1 mechanism. Different players in the same game. It's not hard, not a big deal. My advice, cover up my do my examples yourself by cover up my answer and then see if you get it right. Do that a few times and you master the SN1 reaction. Five, four, three, two, one. Energy diagram. Now, the energy diagram for SN2 was much simpler. It was a one-step reaction, what they call one-hump reaction. SN1 reactions are a two-hump reaction or a two-step mechanism. The first step is the rate-limiting step. It's the slow step. Formation of the carbocation is slow. So what will happen here is the leaving group will leave, forming your carbocation intermediate. So this reaction has two transition states. Transition state 1, transition state 2. Transition state 1 will look like this, where R can be any alkyl group. So that's transition state 1. Or the leaving group is leaving to form the carbocation. That's transition state 1. You form the reactive intermediate, the cation. Intermediate 2 will be when the nucleophile attacks the R+. The nucleophile in the SN1 case is the solvent. So intermediate 2 would be R. Oops. That will be the transition state number 2, where the nucleophile and the R group are making their bond. So this is a two-step reaction, has two energy humps, it has two activation energies, but only one of those is rate determining. And the rate determining step is always, always, always the hump that is the highest one. In other words, the hump that has the highest energy. That's the rate limiting step, the slow step in the reaction. So the speed of the product formation is determined by that step. And in the SN1 case, it is the formation of the carbocation that determines how fast these reactions will go. Now, what determines the rate of an SN1 reaction? The carbocation formation. So doesn't it stand to reason then that the more stable a carbocation is, the faster it would form? In other words, if you're more stable as a cation, wouldn't you form faster than someone who wasn't stable as a cation, for example? So we know already that tertiary carbocations are the most stable. So tertiary halides react the fastest in SN1 reactions. We know that the next stable version is the secondary cation. Tertiary cations, then secondary cations. So secondary cations are less stable than tertiary, but more stable than primary, which are more stable than methyl. So let's just draw this out. And secondary. And then primary. Should be cation, not anion. And then methyl. So this is the order of stability. So now, to make that carbocation, you can have a alkyl halide, right? Let's just say bromide. And let's just say fast. To make this one, say not so fast, or not as fast. Okay, now let's do this one. So to do that one, you'd have to have a primary halide. And let's just put Br there too. That's got to do that. Slow. If at all. It may not even occur at all. And this one has to come from a methyl halide. No. Let's just put no. It doesn't happen. That never happens. Okay, forming a methyl carbocation is extremely slow, likely never to happen. All right. So now let's think about this for a second. Tertiary halides react the fastest because they form a tertiary carbocation. Secondary halides react next fastest because they form a secondary carbocation. Primary forms very slowly because it forms a primary carbocation. And methyl basically doesn't form at all because it forms a methyl cation. Now, maybe it will work, but not likely. Okay? So that's all about the tertiary, it's all about the cation stability. All right? So if you can form a stable carbocation, you're going to form rapidly in the SN1 reaction. So in other words, tertiary is fast, secondary is fast, but not as fast. Primary is slow, methyl is very slow. What about cations that can resonate? Well, allylic cations will react fast. Allylic halides should react fast in an SN1 reaction because they can resonate. Same thing with benzylic. Benzylic halides should react fast because they can form a carbocation that resonates. So allylic and benzylic are fast as well. So allylic halides are fast, as are benzylic. They're also fast because they can form carbocations that resonate. Okay? So this is important to keep in mind. Solvation effect. Oops. Solvent effect or solvation effect. 5, 4, 3, 2, 1. Solvation effect. Now, just like in the SN2 reaction, the SN1 reaction is dependent on solvent. SN2 wants polar aprotic. SN1 wants polar protic. Methanol, ethanol, water, amines to a lesser extent. So let's think about what happens when you put a alkyl halide in a polar protic solvent. So let's just have our friend tertiary butyl halide and a bromide, put it in methanol, and we know that we're going to form the carbocation. That's the first thing that happens. There. Now, why would that happen? Why would the bromide leave? Well, the only way the bromide will leave is if it has some type of positive charge to interact with. Things don't just leave as anions or cations unless they have something of the opposite charge to interact with. That's just how it goes. So in other words, the polar protic solvent, which don't forget, let's just use methanol, delta negative and delta positive, right? So we're going to get ion dipole interactions. So let's have the bromine, or bromide, excuse me, can get surrounded. Oh, don't forget bromide is negative. Here we go. There it is. Can get surrounded by the methanol. Specifically the hydrogens on the methanol. The protic hydrogen, the delta positive hydrogen. Let's be clear. So now there'll be more than the 4. I just drew 4 to prove the example. So now that bromide has a solvent sphere around it, helping to solubilize it so that it will not react backwards with the tertiary carbocation, because the bromide will want to go back to that carbon. But if you can give it another positive environment to associate with, that bromide will not go back to that carbon. And don't forget, the bromide is doing this. The bromide is negative. The carbon is also going to do it. So now the negative oxygens will associate with this carbocation. So the oxygens are delta negative, don't forget. So they're going to give that carbocation a negative environment to associate with. And eventually one of those oxygens will form a bond with that carbon. They will slam into that carbon in the right orientation in order to make a bond occur. But that's what the solvent is doing. It's allowing the ions to separate. It's allowing ionization to occur because they can give the ions the opposite charge that they need to survive in solution. And of course, because carbon has a sextet, eventually one of these oxygens will make a bond with it to alleviate that sextet, because this is a very highly reactive intermediate. And bromide won't react at all. It'll just be an ion in solution. It'll be just hanging out, doing its thing. Now, we have to discuss a little bit about the structure of the carbocation. So now we need to discuss a little bit about the structure of the carbocation. So when you start out a reaction, you start out with an alkyl halide, which is going to be sp3 hybridized, which is going to be tetrahedral. I can do a little better than that. That's fine. So more or less tetrahedral. Okay? Now the leaving group's going to leave. And that's going to give us a reactive intermediate that is a carbocation, which is a carbon with a sextet. Now that is going to be trigonal planar. So you go from being tetrahedral to trigonal planar. You go from being sp3 to sp2. So that's important. You go from being sp3 tetrahedral to sp2 trigonal planar. Now if we think about that, and maybe we should just draw out the orbitals here. There we go. So there's my trigonal planar. But now let's draw in that p orbital. There we go. So the p orbital is there. And the p orbital is not bonding. It's an empty p orbital. There are no electrons in it. It's just there. So now this has serious ramifications. Because now the nucleophile can approach from the bottom or from the top. Now in this particular example, it's kind of irrelevant whether it attacks from the top or the bottom. You'll get the same product. But you need to understand that this p orbital is where the electrons are going to go. So the solvent, say the methanol or whatever, can attack from the top or the bottom. Or the bottom. It can happen 50-50 because the top is not different than the bottom. They're the same. So the attack from one side or the other, 50-50. So it doesn't really matter in this example. But where does it matter? It matters if the alkyl halide is chiral. It matters if the alkyl halide is chiral. One more time. It matters if the alkyl halide is chiral. Let's see an example of that. So let's see an example now where we have a chiral alkyl halide. Now, what you'll get from this reaction is you'll get that one plus that one. So you start out with 1, 2, 3, and 4. So you start out S, and you end up 1, 2, 3, and 4 with S and with R. 50-50. Oops. You get S and R 50-50. Now don't forget, carbocations are sp2 and have an empty p orbital. sp2 is trigonal planar, so it's flat. So here's what happens. Of course, the leaving group leaves. Everybody's already aware of that. Everyone's, I think, comfortable by now. The leaving group leaves. And it's going to form the carbocation. Now I'm going to draw the carbocation as best I can. Trigonal planar. So there's the ethyl group. Here's the methyl group. And there's the hydrogen. Now don't forget, there's the p orbital that runs top and bottom like that. The p orbital runs top and bottom, and the p orbital is positively charged, or the p orbital is empty. Let's say it that way. The p orbital is empty. Now, that means the methanol can attack from the top, or the methanol can attack from the bottom. 50-50. Methanol can attack from one side or the other 50-50. And when it does that, you end up with 50% of one enantiomer, 50% of the other enantiomer. You get a racemic mixture. That's the ramifications of doing SN1 reactions in polar protic solvents. If they're chiral, if they're chiral at the alkyl halide position, they will lose stereochemistry. They will racemize completely. So now let's address the carbocation stability. So carbocations use inductive effect and hyperconjugation to achieve stability. So let's talk about that real quick. So here's our positive carbon. And I'm going to draw a tertiary one. Remember, induction is pulling electrons through the sigma system. That's induction. So what's happening then is this carbocation is attracting electrons through the sigma system like that. It's pulling electrons towards the center. It's pulling electrons towards that carbocation. That in turn pulls electron density from these hydrogens. So I'm not joking when I say these hydrogens are all delta positive. Now I'm just going to draw on those three, but all of the hydrogens on this molecule are delta positive. All right? That's an important concept for when we talk about another type of mechanism called E1. All right, so that's one way carbocations stabilize themselves is through the inductive effect. The second way, which is more important for today's lecture, is the hyperconjugation. So here is our here are the molecular orbitals for I'm only going to draw one. I'm going to leave the other ones not drawn out because it gets a little messy. So here's the empty p orbital right there. So remember, these are electrons. There's electrons in here, right? Hyperconjugation says that these electrons are being drawn over to that p orbital. They're being attracted to it. Because remember, the bond is just a pair of electrons. That's all it is. So that pair of electrons is being attracted over through space to the empty p orbital. Why? Well, very simple. This is positive. These are negative. They're being drawn over. They're being attracted. They're saying, come to me and I will give you stability, kind of thing. All right? That's hyperconjugation. Now you have to keep this in mind for what I'm about to tell you about. Because I'm about to tell you about rearrangements. Rearrangements occur a lot in SN1 reactions because carbocations will rearrange if they can form a more stable carbocation. Let's see the most awesome example I can give you about this. So here we have a secondary halide. We're setting up for an SN1 reaction. But you don't get the expected product. You get this, where the ether is on this carbon. And a methyl group has changed locations. So this is interesting. What happened here now? Let's think about this. Well, when presented with a question and something's funky, don't automatically think the question's wrong because it's probably not. Think about mechanism. Whenever I have a problem that I can't figure out in chemistry, I do mechanism. I resort right down to the mechanism and I don't think. I just do what I know is right. I do the mechanism. So I know it's a polar protic solvent. I know it's SN1. I know that the reaction has to start this way. Don't think about it. Just do what you know to be true. And hopefully we can figure things out as we move along. And almost always you can. carbocation. So this is a secondary carbocation. Now remember hyperconjugation. These electrons from this carbon over here are being drawn over this way towards this cation. Because there's a cation here, these are negative. They're being drawn over. They're being attracted, if you will. Now, that attractive force is pulling them over here. These electrons are being pulled to the right. Just because it's a through space, negative here, positive there, they're being attracted. Now, as that's occurring, this carbon is becoming more and more positive, right? As it's occurring, as these electrons are being pulled over this way, this carbon is becoming more and more positive. And the energy of the reactive intermediate is dropping. It's becoming less reactive, less energy. So what happens, and how I want you to draw it, is these electrons eventually find their way over to that carbon and make a bond. They slide over. It can only happen by one atom, though. It doesn't happen over 4 or 5 atoms. Only adjacent atoms can do this. So anything attached to this carbon potentially could rearrange. Anything attached to this carbon potentially could rearrange. But you always rearrange to more stable. You never rearrange to less stable. That never happens. Okay? Always rearrange to more stable. So now we have this carbocation. And the methyl has moved from here to there. Cool, huh? And now I think everyone will believe that it makes sense. That now the methanol will attack that carbon because it does have a carbocation. Oh, by the way, this is a tertiary carbocation, right? So we went from secondary to tertiary. That's allowed. From less stable to more stable is allowed. Going from more stable to less stable is forbidden, so don't do that. And that completes the mechanism. So the blue steps, the steps with the blue methanol, those are steps I've already shown you. So hopefully those are second nature by now. So those are rearrangements. Now methyl groups can rearrange, rings can rearrange, hydrides can move. So this could have been an H that I moved from here to here. As long as you're going from less stable to more stable, rearrangements are possible. So methyl groups you'll see move, hydrogens you'll see move, you'll see rings expand, you'll see all kinds of interesting things with rearrangements.